So overall, the broad sort of topic in this set of notes in this chapter is oblique triangles. Oblique triangles are just triangles without a right angle. So we know how to deal with, we know exactly what to do if we have a right triangle. We have Pythagoras and we have SOHCAHTOA. So what we're going to do now is just specifically examine what do we do when Pythagoras and SOHCAHTOA are no longer available to us? It's so funny. I decided to write this out and then here it is. It's almost like I planned ahead and then didn't even know I had a plan. Okay. So there's 4 cases we're going to look at. The law of sines will allow us to address the first 2. So each of these 4 cases, they're just the 4 cases that will define a unique triangle. The general scheme of this is that we need 3 pieces of information, at least one of which has to be a side. If the only thing we know are all 3 angles, then clearly that doesn't uniquely define a triangle because you could just scale it up or scale it down, right? There's infinitely many. So the law of sines tells us that in any triangle at all, that if you take side A and divide by sine of A, side of its opposite angle, and we adhere to that convention, by the way, that we use the lowercase letter as a side opposite the uppercase letter angle, that when we take that ratio of a side length divided by sine of its opposite angle, that ratio is always the same. And that's what this sort of set of equations tells us. We're going to begin just by deriving this fact. We can do it using some geometry and SOHCAHTOA, mostly. So we start by doing one. Okay, this is ridiculous. Why will you not? Okay, guys, sorry. Hold on. I wonder how much of my lecture videos are taken up with me begging my tablet to cooperate. Okay, we begin. I can do this. We begin by drawing a perpendicular down from this point at the top. We can do it. And we'll call this h, is for the height of the triangle. This is a right angle because it's a perpendicular by design. Now we use SOHCAHTOA. Let's use SOHCAHTOA over here for angle A, and SOHCAHTOA tells us that sine of A opposite over hypotenuse in this case. What does that look like? Oh yeah. H over B, yeah, because we're using this right triangle here. And we can solve this for H. We get H must be equal to B times sine of A. Now let's use SOHCAHTOA again over here for angle B and for this other, sort of the right triangle that's side by side, the other one. What do we get for sine of B? Say that again? Yeah. Yep, H over A. And if we solve this for H by multiplying both sides by A, we get H is equal to A times sine of B. So these 2 facts, take these 2 equations, right? We have these 2 different expressions for H. H is obviously equal to itself. So we get that, let's see, B times sine of A is equal to A times sine of B. These have to be equal to each other. And now we can divide both sides by the product sine A times sine B. Do some canceling. The sine of A cancels on the left side. Sine of B cancels on the right side. And we get B over sine B is equal to A over sine of A. And there is the law of sines established using the angles A and B. We could likewise establish this equivalence if I drew a different perpendicular. Draw the perpendicular from a different angle, and you can establish the same thing. So really the law of sines comes from finding a way to make a triangle that SOHCAHTOA will apply to. Make a right triangle where we did not start with one. And when we do that, when we start with SOHCAHTOA, then we derive this set of equations that is true for all triangles, not just right triangles. Let's get some practice using this fact. When you're doing some solving, you should always remember that you can use this as like a common sense check or a sanity check at the end of a problem. The longest side will always be opposite the largest angle, and the smallest side will always be opposite the smallest angle. So that's one thing that you could check at the end. We don't have, we can't check with Pythagoras anymore, and we can't check with SOHCAHTOA anymore because these are not right triangles. We can, of course, all the angles have to add up to 180 still. So we're going to begin with an example that is the second case where we have two sides and the angle opposite one of them. Look, because of the type of equations, because of the expressions that are involved in the law of sines, here's what we must have in order to be able to use it. We must have like a matched pair. We've got to have a side and an angle opposite that side. And then we'll have like another mismatch pair, right, where we know one but not the other. Like we have to be able to completely fill in one of these fractions in order to be able to use law of sines. So if we know two sides and the angle opposite one of them, like say in this triangle that they provided for us here, we have these two sides. Angle A is this angle opposite one of them. Here I have this matched pair, right? That means I can fill in the fraction, the ratio completely for A over sine A. And then we can, what would be the next thing we could solve for, or the other fraction we want to involve? B over sine B, because this is the incomplete pair that we have, right? So the first thing we need to do here, really, there's not much of a choice. The first thing we need to do is solve for angle B. So let me move this over so I have a little bit more space. So A over sine A is equal to B over sine B. Now we'll plug in the stuff we know. 20 over sine 65 is equal to 15 over sine B. And what we will do first is just solve this equation for sine of B. Right? We'll worry about finding B after, but if I can get sine of B by itself, we'll be in pretty good shape. One option we have, especially when using the law of sines, because it is just one fraction equal to another fraction, is we can set those cross products equal to each other. So these products are equal to each other, meaning we have 20 times sine of B is equal to 15 times sine of 65 degrees. And now to find sine of B, we need only divide both sides by 20. And I just carry all this down with me. Like if you like doing the intermediate calculations, that's totally fine. You'll notice I'm just sort of carrying the whole thing through. Now, whatever this is, 15 times sine 65 degrees divided by 20, is some number, right? Like, so we know the value of sine of B. And if we know the value of sine of B, how do we get the angle B? Arcsine. That's what arcsine does. So angle B is arcsine of this stuff. And you can really just put this whole thing in your calculator in one go. Got to be a little careful with your parentheses. Make sure you're in degree mode. So we have, is it 15 times, whoops, hold on, I'm getting ahead of myself. Arcsine of 15 times sine of 65. I'm making sure that I close the parentheses on that sine function. And then I'm going to divide by, was it 20? And then close the parentheses on the arcsine. And I get 42.82. Or 40, see, the original angle was given to the nearest tenth, so I'll call it 42.8 degrees. Yeah, because it says solve the triangle, and when this says solve the triangle, that means fill in anything that's not given. At this point, though, finding C isn't too bad. What could we do?
180 minus both A
Yeah.
and B.
Yep, exactly. So angle C is 180 minus 65 minus 42.8. And I get 72.2. How's that so far? We have one thing left to find. Yep, we need side C. But now that we know angle C, we can use law of cosines. If we're solving for side C, we have to use the version that has C over sine of C. But that side C, that angle C is a known quantity now. So we will use this. Now, you could, because we know the other angles, use either side B and angle B or side A and angle A. I think by now you know I'm in the habit of trying to use given information whenever possible. I think it's totally legitimate to use B and angle B, so whichever way you prefer to do it. But we set up our equation. C over sine C is equal to, I'm going to use A over sine of A. So C over sine of 72.2 is equal to 20 over sine of 65 degrees. And if we want to solve for side C now, I wouldn't do you could do the cross product still, but it's kind of faster just to multiply both sides by sine of 72.2. So we get C is equal to 20 times sine of 72.2 divided by sine of 65. And again, just when you're using the calculator, make sure that you close out these parentheses before you divide by sine of 65. I guess 21.0. How's that? Okay. Quick check. Our largest angle is angle C, and side C ended up being longer than either of the two given sides, so that jives with what we found. That seems about right. Another? Oh, yes. Oh, look how much space I gave. I didn't have to smush that over on the side, but in my previous draft, I did not give it as much space, so that's why I was... Okay. Got lots of space here, too. All right, so now we're going to do one where we know two angles and one side. Again, we can use law of sines as long as we have a matched side angle pair. And for us, that would be side C and angle C, right? Now, if I'm going to start by solving using law of sines, what would we do first? What would we go for first? What are we going to try to find first?
B.
Yeah, B, the side opposite this other known angle. So, setting up our equation, we know that B over sine B is equal to C over sine of C. So we have B divided by sine of 108 is equal to 59 divided by sine of 25. We can solve easy enough just by multiplying both sides by sine of 108. So 59 times sine of 108, close the parentheses and divide by sine of 25. And we get 132.8. And this would be in feet. It would inherit the same linear units. Now what?
Find angle A.
Find angle A, and in fact, we have to. I mean, you know, there's angle A and side A that are both unknown. We have to find angle A first because in order to use law of sines, if I were to find side A using law of sines, you know, I'd have to have the opposite angle in order to even begin that. So we could find side A, and that one's pretty easy because we could just subtract from 180. So we get 47 degrees. And now we can find side A using law of sines. So A divided by sine A equals, and again I usually use the given pair of information whenever possible, so this would be 59 divided by sine of 25. Oh, and I know sine of A, so A over sine of 47 is 59 over sine of 25. Multiply both sides by sine of 47. 102.1 degrees. Oh no, feet. This is the side. Huzzah. Questions on that example? Okay. Okay. All right, so now this is the fun part when working with the law of sines. There is a scenario that is ambiguous. Sometimes they could give us information that might define two triangles. They might give us information that could not possibly define any triangle at all. And this is the case where we know two sides and the angle opposite one of them. I think we called that case 2. It's kind of like this one here. No. This one here, two sides and the angle opposite one of them. So part of the problem, or part of the potential hazard with the law of sines when you're using it to solve for an angle, is that the arcsine function will never, ever, in a million years, return an obtuse angle. The angles it will return are always acute. So if you're setting up your triangle and you know the angle you're looking for is obtuse, it simply will not return that angle that you're looking for. So we kind of have to have an idea of what kind of angle am I expecting to get. If I know that I'm looking for an obtuse angle, I'm gonna, that's a second quadrant angle, and I can find the acute angle and use the reference angle, right? Just like we always find a second quadrant angle. But we also need to know when we're in this particular situation, because the two sides and the angle opposite one of them, sometimes they only define one triangle. I mean, the first example we did, there's only one triangle that satisfies that given information. So in these cases, I'm going to assume, I'm just calling the known angle A, and we know side B, and we know side A, right? So our match pair is angle A and side A, and I've drawn the other given side on this side, on the top side, rather than the bottom. And whenever I'm trying to draw a triangle with information, I adhere to this convention. I just find it helpful, maybe just because I'm used to it. But here's the idea. It all has to do with, is this side A that they gave us, is it A, long enough to even make a triangle, right? Like our triangle could, or this side over here could just be so short. Like if we know B and we know this angle, then this opening is determined, and we know where point C is. So if the side opposite this given angle is too short, it won't even make a triangle, right? It has to be at least as big as this, what would be the hypotenuse if this were a right triangle. So that's what we start out doing, is we say, okay, if this were a right triangle, what would the hypotenuse be? If A is less than that, we say there's no triangle, and we move on, right? We just dispense with that problem. If it's precisely equal to H, we say, oh, look, it's a right triangle, and we do whatever we do with right triangles, and then we're done. If it's bigger than H, then we know we can make a triangle, and we need to figure out, can we make more than one? So the case where we can make more than one essentially looks like this figure here. So A is longer than H, right? It's what allows it to swing over here. But A is also not bigger than B. If A is bigger than B, then the only way we could do this is to swing it out this way and see where it hits. But if A is bigger than H but less than B, I could draw that side A down this side, or I could kind of swing it over here and have it intersect side C on this side. That's the ambiguous case. That's sort of the, where we kind of have two triangles to solve. And we're going to do some examples that'll help us kind of figure out what, get a little practice trying to determine which of these cases we're in. So in example 4.3, we're given, so a lot of the problems, by the way, look like this. They don't draw the triangle. They say, they give you a list of information, and just with the understanding that side A is angle opposite A, and likewise, we try to make our own sketch. So here, they say angle A is 26 degrees. So what does that look like? Maybe that. Right, I'm not trying to draw a complete triangle right now, but this is 26 degrees. Side B is 41, so that'll be the adjacent side here on top, 41 centimeters. That's given. And then side A is 25 centimeters. I'm not even drawing it all the way right now. My question is, I'm not going to assume this makes a triangle yet. My first question is, can this make a triangle? So what I'm going to do is drop down this perpendicular, which is H, and I'm going to figure out what would H be. This point at the top is point C. B might be somewhere over here if this even is a triangle. So let's find H. Because H is that perpendicular, we find H using SOHCAHTOA. So we know that sine of 26 degrees is H over 41. And that means that H is 41 times sine of 26 degrees. $17.97, or yeah. It's nothing that we're going to use in our further calculations. Oh, 17, not 19. But knowing that value and comparing it to the value for A and B is what's going to help us determine, can we even make, so first, can we make a triangle with this? You're nodding your head yes. Why?
A is longer than H.
Yeah, A is longer than H, right? H is the absolute minimum in order to even make a triangle. So we know we have at least one triangle. Then the next question is, do I have one triangle or two? And what do we look at to figure that out?
That A is longer than H.
Well, A is longer than H means I can at least make a triangle. Now we're trying to figure out, is there just one or are there possibly two? And what we have to compare it to in order to answer that question is this side length B. So if A was in fact longer than B, we would know there's exactly one triangle. But since A is in between the two, right, what we know is that, let's see, we're in the situation where H is less than A and A is less than B. A is right in the middle, and that means that we have two triangles. So now we know it'll make a triangle, right? So like, let's say here's B. The way I've drawn it, right, just by virtue of kind of swinging this side out this direction, I've drawn it here so that B is acute. This is one of those solutions where angle B is acute. So let's solve that one. This would be the one that we would naturally find if we just imposing the law of sines on this. We have to do nothing special than we've done in the last couple examples. So let's see, we're going to use our pair of information. Our pair of known values is side A and angle A. So A over sine A equals, and we'll find angle B, so that would be B over sine B, and then we'll plug in what we know. And angle B should be the only unknown once we do that. So we have 25 over sine of 26 degrees equals 41 over sine B. We will solve for sine B first, like we did in the first example that we worked through. We can set the cross products equal to each other. And divide both sides by 25. And since we know what sine B is, we just use arcsine to get angle B. Oh, thank you. Divided by 25. So 45.97 degrees. Or I guess we could call that 46.0 for rounding to the nearest tenth of a degree. Alright, so we know angle B, side B, angle A, side A. What's next? Yeah, we'll find angle C first, because that's what we can find. Just subtracting from 180. $108. And now that we have that angle, we can use law of sines one more time to get side C. So C over sine C is equal to A over sine A. This means that C is equal to A times sine of C divided by sine of A. And then I'll just throw in the numbers here. $25. So 54.24. That would be in centimeters, I think. So there's this I mean, we're not quite done with this problem because we have another whole triangle to solve for, right? We started out this problem figuring out how many triangles could we draw with this given information. And we said, well, A is certainly long enough to make a triangle because it's larger than this height of the triangle, but it's shorter than side B, that adjacent side. And so that puts it in this sort of sweet spot where we get two possible triangles. Now, here's how I kind of drew this side kind of angling out in that direction to get to point B, but we could easily have drawn the triangle, drawn that side to bow out this way, kind of inward. And so that's the other triangle that we're going to solve, is the one that looks like that. So this one has an obtuse angle B. So here's the 26 degrees given, the 41 centimeters given. And now here's an obtuse angle B, which I'll call it B prime. And this one's C prime, because they're not the same, right? They are different measures. Side A is 25, that's given. And so we need to find angle B, angle C, and side C, little c prime, I guess. Now, we're going to sort of reap the fruits of our labor in part one because, you know, we started talking about this ambiguous case by observing that inverse sine will never give you an obtuse angle. So it begs the question, how do we get the obtuse angle here? So once we solve for the triangle where we found the acute angle, the obtuse angle is just the supplement to that angle. So we just subtract it from 180, and that's what gives us B prime. So 180 minus the 46 degrees that we found. And that gives us 134. So there's an angle that we know. And if we know that, that means that we can find angle C prime. By subtracting these two angles from 180. $20 degrees. So for the other triangle, we only need to use the law of sine once, and that is to find side C. Since we know the angle opposite side C, we can find side C using C divided by sine C. Basically, the same process. We're just doing the same thing we did up here, right, when we found that side. So C prime is A times sine of C prime divided by sine of A. Plug in our known values. .5 centimeters. How's that? So this is sort of this example is basically, I guess, a worst case scenario, if you want to look at it that way, in terms of the amount of work that could be required in solving one of these. A lot of these problems, there might just be one triangle, or no, if there's no triangle, then, that's the easiest situation, right? Questions on this example before we do another one? Okay. So let's do another one. Let's solve this triangle. They give us angle A is 62 degrees. So something like that. They give us side A, so that's the opposite side, and side B, which is an adjacent side. So this would have to be side angle C up here. 415. I know that I am in the ambiguous case because they've given me one angle. They've given me two sides and the angle opposite. So I have one matched pair, and then I have another stray side thrown in. That's basically when I know I'm in one of these cases, right, where I don't know how many triangles that this could define, if it even defines one at all. And so as soon as I know I'm in one of those scenarios, I know that I'm going to need to determine if this can even make a triangle, and if so, how many. So the good news, oh no, is there good news? I don't know, let's find out. Let's see if this makes a triangle. Is there good news? That's probably nothing you want to hear. All right, so before this is not to do with this particular example, but a good particular note. We're starting by finding the height of this triangle, right, to see if we can even make a triangle. But one scenario that would involve very little work, if any, at the outset, is if this opposite side were longer than B, I would be guaranteed I can make a triangle and that there's only one. So there'd be no testing, right? Because this is less than B, I need to see if it's at least as long as it needs to be to make a triangle. All right, so there's H. How do we find H?
Sine 62 is equal to H times 855.
Yeah, so sine of 62 degrees is H divided by 855. This right here, this scenario, when we know that we're in the ambiguous case and we're not sure if we even make a triangle, so we got to find the height. This is like the only scenario where you're going to use SOHCAHTOA in an oblique triangle type of problem, right? So if you find yourself using SOHCAHTOA to solve for the actual pieces of the triangle that they're telling you about, something's wrong, right? SOHCAHTOA only applies to a right triangle, so it's only because we drew that perpendicular that we have a right triangle. So we know that H is 855 times the sine of 62. So 754.92. This would be in meters. What now?
Compare side A to the height,
Yep.
and side A is less than the height.
And what does that mean?
It can't be.
Yeah. I would say this is the opposite side of the spectrum in terms of how much work required to solve one of these. No triangle. All right, I'm done. Whenever I am doing one of these types of ambiguous cases with the law of sines, I picture this angle here welded shut, right? Like it is fixed at 62. I don't know this angle, so at the top at angle C, like that's a hinge. It's just swinging. Right, and I'm trying to figure out, is this long enough? If this just sort of swung down here, would it actually be able to hit this opposite side? Nope. Nope. Fun? Yes.